Hi everyone. So what I'm talking about today is this example, an integral where we can't directly apply Cauchy's integral theorem in the way that we've done in the earlier easy examples. And I want to talk about the qualitative difference between those things, and then to show how we can come up with a method of solution that involves a mixture of a clever application of Cauchy's integral theorem and the Cauchy-Goursat theorem. So to remind you, the Cauchy integral theorem says that if you have this setup where you have an open, simply connected domain U and a function f that's analytic on U, and then inside that you have a closed contour, simple closed contour C, and a point W contained on the inside of C, then you know the value of f at W, that is the value of f at the interior, or for interior points, is equal to this strange looking 1 over 2 pi I times an integral where we've taken f and then divided out Z minus W. I pointed out in an earlier video that the intuition from this comes from the fact that you are thinking about f as having a power series, and then you're inducing a singularity in the function by dividing through by one copy of the powers of the polynomial that you've created with the power series. And ultimately, this relies on the fact that with this setup, we showed earlier, and we're going to use this fact again, we showed earlier that anything that looks like this you can show directly is equal to 2 pi I, where C is oriented in the positive direction, right? So the idea here is that for functions of this form, where we have a function that has a singular point, or an asymptote, on the inside of its domain, that if you just do the substitution where Z is equal to W plus R e to the IT to make this contour into a circle, that you can substitute this in, and what will come out the other side is 2 pi I. So in some sense, what you're measuring here is how the contour wraps around the point where the asymptote is. Okay. So we did this earlier, and we did this directly. So the idea is that I want to be able to do some sort of clever rearrangement of this function so that I can apply Cauchy's integral theorem to it, to be able to say this, which is really just a beefed up version of this example. In an earlier example with a smaller contour, what we did was we can think about the function 2z plus 1 over z times z plus 1. I can think about that function as either 2z plus 1 over z plus 1, or I could think about that function as 2z plus 1 over z plus 1, and then divide it by z. And after this rearrangement, if in either case this function or this function happens to be analytic inside the contour that we're integrating around, then I can directly apply Cauchy's integral theorem. Problem is, in the setup that we have right here, so this is the sort of typical Cauchy integral theorem algebra trick. The problem in the setup that we have here is that this function is not analytic at z is equal to 0. And this function is not analytic at z is equal to 1, negative 1. And so in both cases, we have the issue that to apply Cauchy's integral theorem, I need the f of z to be an analytic function inside the domain where I'm integrating. This function and that function are not analytic inside a circle of radius 2. And so the Cauchy integral theorem doesn't actually apply here to this rearrangement or this rearrangement as they do in earlier examples. The art of constructing contours that do what we want is sort of the core of contour integration and complex analysis. Very frequently, we don't just immediately turn to a parameterization of C. We have some contour that we're interested in integrating around, but we can't do it directly because we don't have access to any of the tools we need to do it. In fact, if I try to do this one directly, which is pretty easy, you'll see that the direct parameterization gives you a function that's very difficult to work with because of this mixture of z squareds and z's and z's and dz's. There's going to be e to the it's running all over the place. It's not necessarily going to be straightforward to integrate. So in a situation like this, instead of immediately turning to parameterization, my first idea might be, maybe I can construct a contour that this contour is part of, and yet I know something about what the big contour behaves like because I have these two theorems available to apply to it. Okay, so let's talk about the function f of z here, written three different ways. And we're going to evaluate the integral of this function around two different contours to see if, what situation we actually can apply Cauchy's integral theorem to. And then we're going to try to use that information to build a big, sophisticated contour that actually answers the integral question we're after. Okay, so let's suppose that I draw the complex plane C, and I'm going to mark the asymptotes of this function on the complex plane. So this function is not defined at either 0 or -1. So there's an asymptote right here at z is equal to 0, and there's an asymptote right here at z is equal to -1. So what I'm going to do is I'm going to draw a contour, and then I'm going to try to evaluate the integral of this function around that contour. So I'm going to call this contour, so we'll make a circle here, C0 for a circular contour that goes around the asymptote z is equal to 0. Okay, now notice that on this set, that function, this function is analytic. So you can imagine that you can surround this contour with an open set U, and inside U, that function is analytic because the only place where this function is not defined is at z is equal to -1. Z equals -1 is outside of the circle that I've written around z equals 0. Why would we do that? Because that means that if I take the integral around C0 of 2z plus 1 over z squared plus z dz, I can use the trick where I rearrange that function into a piece that absorbs the asymptote and the rest of the function, which is analytic on the domain that we've defined here. So this is equal to the integral on C0 of the function 2z plus 1 over z plus 1 over z minus w, or 0, dz. This is just algebra. I've done nothing here. This function and this function are the same. But to this integral, the Cauchy integral theorem applies because this function is analytic on C0, or on, we'll use Johnston's language here, analytic inside and across C0. I can find an open set that completely contains that circle C0 on which this function is analytic. And that means that the Cauchy integral theorem applies here. So immediately I can say, well, this must be equal to 2 pi I times f of the w value, which is right here, must be equal to the integral of f of z over z minus 0 dz. That's what the Cauchy integral theorem tells you, is that you know that this must be true. Now, what I've done is I've multiplied both sides by 2 pi I so that I can evaluate the integral directly, but this integral must be equal to this by the Cauchy integral theorem. Now, of course, I know what f of 0 is because I can plug f of 0 into this function. Not this function, but this one, because this is the f of z in this case, right? For this particular problem, f of z is equal to 2z plus 1 over z plus 1, and so f of 0 is 1. And so this integral around that contour by the Cauchy integral theorem is 2 pi I. Now that doesn't solve the problem because the integral that we were interested in figuring out here was the integral where we had a circle of radius 2, which contains both of the asymptotes. But let's store this fact that we know that the integral around z0 of this function, by careful algebraic manipulation and trickery, we can apply the Cauchy Integral Theorem, and we know that that integral is 2 pi I. So let's do the same process, but now we're going to wrap a circle around z is equal to minus 1. Okay, so for this version of the problem, we're going to put a circle around this. So if you had a contour c minus 1 for the fact that it surrounds the asymptote at minus 1 of the function, then certainly it's the case that you can find a circle around c1 that does not include z equals 0. That's not hard to imagine. So that gives you a domain U. And the idea here is that on this domain, I can do the same algebraic trick, but now not with this function, but with that one. So the asymptote behavior is going to be absorbed into the bottom of this. What do I mean? I'm going to evaluate the same integral. I'm going to start this integral again, but on a different contour. So the integral around c minus 1 of 2z plus 1 over z squared plus z dz. Well, I can algebraically rewrite that as 2z plus 1 over z plus 1 dz. And then to make it extra clear what's happening, instead of z plus 1, I could have written this as z minus negative 1. Now, why did I do that? Because this function is analytic on u. Because the only problem this function has is that z equals 0, and z equals 0 is not contained in the interval, or in this domain u. Since z equals 0 is not contained in the domain u, this function is analytic, and so the Cauchy Integral Theorem applies. So by the Cauchy Integral Theorem applied to the function f of z is equal to 2z plus 1 over z, and a w value of minus 1, it must be the case that this integral is equal to 2 pi I times f of minus 1. What is f of minus 1? F of minus 1 in this case is, you put a minus 1 in here, you get minus 1. Minus 1 divided by minus 1 is positive 1. So once again, we get 2 pi I. So this integral evaluates to 2 pi I on that contour. Okay. So now basically the picture is that we know how to integrate the function on a circle that wraps around z equals minus 1. And we know how to integrate the function on a circle that wraps around z equals 0. So how can we use this information to figure out what the integral of this function is on a circle that surrounds both asymptotes? And this is where we have to be a little clever. Let's talk about how we can use the fact that we know the value of these integrals to figure out the value of that one. So this contour where the radius of z is 2, or the modulus of z is 2, we're going to call that contour C. So C is the contour of interest, which is the set of points z, so that the absolute value of z is 2. Now the issue is I can't use the algebraic tricks that I use to figure out these integrals, because that contour contains both of the asymptotes of the function. This contour contains both z equals 0 and z is equal to minus 1, which you can see if you plot it down. If you have z is equal to 0 and z is equal to minus 1, and then you take the contour of radius 2 around those, so this is modulus of z is 2, then you have a contour that contains both of the asymptotes. So what we're going to try to do is to construct a contour, a fancy contour, maybe, that includes this contour, and that contour as pieces, and then I can use the fact that integrals break up over those pieces to try to evaluate the whole situation. And the ultimate goal is to build a contour not just that has these three contours as part of it, but also a contour that has a simply connected interior so I can apply the Cauchy-Goursat theorem. All right, so the goal is to build a piecewise smooth contour with a simply connected interior that contains this contour and this contour as segments. So here's how you do that. So what we're going to do is we're going to start by doing our contour, C. So we're going to start here, and you can imagine I'm going to separate the lines here, but these line segments that I'm going to draw along the real axis are the same line segment. So we start at a point here and we go all the way around with positive orientation because this is our contour C. So first we do C. Then what? Then we're going to get in here and we're going to head around this point, but I have to get to it. So what I do is I get back here and I come in this way. And Johnston calls this L in. So we get out to z is equal to 0. Then we do the bottom half of the curve around z is equal to 0. Now that almost is the curve. This is like the bottom half of the curve around 0, this contour around 0, but done in the opposite direction. This is a negative orientation, not a positive orientation. So we're going around the curve this way. I'm going to call this C0 negative, which means I'm wrapping around this curve, this the asymptote here, with a little curve that goes around 0, but the bottom half of it. Then I scoot over by doing M in Johnston's language to get myself near z is equal to -1. Then I run that contour all the way around. So this is C -1, but done with the negative orientation because I've traveled in the clockwise way and not the counterclockwise way. Now I need to get back to my curve C so that I've got a complete contained interior. So I go this way. I think about this as being M out. I do the top half of the contour around 0 in the backwards direction. And then I leave on this line, L out. And if I put a little gap right here to really emphasize the fact that this interior, lines are supposed to sit on top of each other. So I'm doing this to suggest why we're taking this approach. I've actually seen this contour called decayed tooth Pac-Man before, which is like a chomper, but his teeth gone. Anyway, so the idea is what? The idea is that each contour we were interested in is contained inside this mega contour. Here's the contour C, which is the integral that we're interested in evaluating over. Here is a little contour around 0, but with reversed orientation. And here's a little contour around -1, but with reversed orientation. Now these two pieces together are going to form the whole contour because that's the way integration works. If I integrate on two pieces, I can stick them together and integrate over the whole thing. These integrals are over the same line segments but reversed, which means they're negatives of each other, which means this integral over of the function over m out and the integral over m in will cancel if I add them because they're in opposite directions. Finally, the interior of this set should be pretty easy to see, is simply connected. If I took this and I sketched out the interior, it's not hard to believe that this has no holes in it. If I drew a loop in here, any loop can be contracted to a point. There's no holes in the shaded region inside this thing. Now that's important because it means on that region, this theorem applies. The Cauchy-Goursat theorem is going to say that the integral of g of z over the red region, over the curve surrounding the red region, is 0. G of z, the integral of g of z dz over the monster contour is equal to 0. because this function is analytic as long as I stay away from its asymptotes. And there's no asymptotes in here. In the simply connected part of the domain, this function is analytic. Okay. In fact, maybe we should be more careful and just actually write the function in here so I'm not confusing with multiple notations. 2z plus 1 over z squared plus z. That function must integrate to 0 on this monster contour because the interior of this is simply connected, and that function is analytic on the interior of this. It's also the case that the integral of 2z plus 1 over z squared plus 1 dz, and now I'm going to call this function g of z again, is equal to the integral over c of g of z, because we do that first. We start here and we do all of c, and then what do? Well, we do the integral over this piece in the opposite direction. So it's going to be minus the integral of c naught minus 1 g of z dz. And then we do m in. The integral over m in of g of z dz. And then what do we do? C minus 1, but in the opposite direction, right? Because we've come in, but we're going the wrong way. We're not going in the positive orientation, so we can write it as minus the integral around c minus 1 of g of z dz. So we've done c, and then L in, and then the bottom half of C0, but in the opposite direction, and then M in, and then all of C minus 1, but in the opposite direction, which is why I'm picking up these negative signs. And then I have to do M out. And then I do the top half of C naught. In the opposite direction. And then I do L out. And we know some stuff about this because I can use integration theory. First is the integral on M out and the integral on M in are connected to the same points to each other but in opposite directions. And so this integral and that integral are 0 because they're equal but opposite. Likewise, L out and L in. I forgot to do L in. C, L in, then C naught, negative. Yeah, so the L in should have been here. L in and L out are opposite. And so they cancel because they're on the line segment but opposite. And then I can glue this piece and this piece together to get the whole integral of the contour around C naught because it's just two segments that together make up a contour around C naught. And so I can rewrite this whole algebraic expression in the following way. This is equal to, well, what's left? The integral over C of 2z plus 1 over z squared plus z dz minus the integral over C0 of 2z plus 1 over z squared plus z dz minus the integral of a contour around -1 of 2z plus 1 over z squared plus z dz. So using the theory of integration in this monster contour gives us this giant pile of integrals that resolve down to this. But on the other hand, the Cauchy-Goursat theorem says that the same integral is equal to 0. So this equation is true. 0 must be equal to the sum of all these. But I know what this integral and this integral are equal to. They're each equal to 2 pi I. I solved that by looking at integrals on the individual contours that went around 0 and -1. And so that gives you the answer to the question. Combining all of this together, we conclude that the integral around C, that was the integral, this was the, sorry, fancy C here. This is the integral with radius 2, that integral minus 2 pi I, which is the value of this, minus 2 pi I, which is the value of that, is all equal to 0. And that means that the integral around that contour is equal to 4 pi I. Now this is typical of how you use these sort of fancy contours to attack questions like this. And the idea is that you try to isolate the asymptotes of the function so that you can apply the Cauchy integral theorem to each individual asymptote isolated, so that you don't have to deal with places where that function is not analytic on the inside of a contour. And it's no surprise, or shouldn't be a surprise, it's no accident, I should say, that the value of this integral turns out to be the sum of the little tiny contours around the asymptotes. That's generally what the approach is going to result in, is that you have a function, you can apply Cauchy integral theorem to contours surrounding the asymptotes and then just add those values together if you're trying to integrate around a contour that contains all of the asymptotes. All right, this takes some practice and some getting used to. So I recommend that you try some of these. They're not so hard once you've got some experience constructing the contours. And again, this could be made more rigorous. We could take limits, and in fact, later on, maybe we will see some integrals where we have to take limits. But the idea here of taking a function with asymptotes that we're trying to integrate and then carefully constructing a contour that surrounds them all. You can imagine that if you had a function with 3 asymptotes and you were trying to construct an integral, a contour that, if you wanted to know this, so if you're interested in the integral around C of some function f of z dz, then the trick is to build a contour that incorporates this and just does this. So this way, this way, this way, this way, that way, and then back out again. And the same trick is going to apply. When you take the interior of this, which is simply connected, you can apply the Cauchy-Goursat theorem, which is going to tell you that the integral on C is going to be equal to the integral around this asymptote plus the integral around a contour around that asymptote plus an integral around that asymptote. So if you called this CA, CB, and CC, the same argument that we just used is going to show you that this is equal to the integral around CA of f of z plus the integral around CB of f of z plus the integral around CC of f of z. The same trick applies.